Welcome to Careless Coder. Today a little PDP11 assembly on the front panel of an 1170. And no, I don't own a PDP11 because I'm not going to pay $315 including shipping just to play with a few switches. And there is stuff on the internet that looks even better. And I don't own a PDP11 anymore. I used to own one, but it was a micro PDP11, not the big 1170. Motherfucker! So I initially wanted to do a video about the game 31 that I implemented in C that Robin from 8-Bit Show and Tell did a video on last week. But it's a bit too much code to explain and I don't want to talk too much. So we're just going to fiddle with some switches on a front panel of a PDP 1170. And I found a really easy way to actually install that after spending an evening to get it to work on Mac OS with code that doesn't compile and that isn't working. And oh my god, why is software so fucking bad these days? Test your fucking shit. Let's jump in. This is actually the third time recording this. First, my audio was completely redlining, even though the VU meter didn't, but only on the playback. And then it had this weird stutter. OBS is one of those notorious pieces of crap software that I'm really starting to get fed up with these days. And just like this build stuff, it was crap. But they have actually a pre-built version that we're going to use. And it looks really adorable, as you can see. So first we need to check if we have a Java runtime, because this runs in Java. We do. And then we use one of their pre-built packages. Make life easy. So we have it for the BlinkenBone. That's a small board computer, which you can also do the LEDs. You have the Pi, like the PDP11. And of course, we have x64. I already downloaded it. So I'm going to copy that where I want to install it. I already have my source code. And extract. Alright, we have a panelism. That's good. So if we go into there, we actually should be already set. So I'm going to start with the PDP 1170 Blinky. And there we go. And that is the Blinky, and you can actually flick these switches to actually speed things up and change patterns. And we're basically going to make a Knight Rider scanner that scans left to right about the same speed, so it looks like an angry kid. But this is a bit small. I don't really like that, and you may run into an issue that I had on a modern Ubuntu, which we're going to discuss now. So if you, for example, hold the system, and yes, in a moment I'll make this bigger. I can actually do that already here. So we hold the system, and if you continue, which is this switch, the cont, you should see step 1. In modern Ubuntu, you get an IO control error. Now, the way how you solve that is actually by setting IO control, setting this to 1. And you can actually set this also in your echo. Oh, you're not allowed to do it like this. Let's sudo -s. And you can also echo dev.tty.legacy TIO control, source control, into your system config. I already had that, so now I have 2. So let me fix that in just a second, otherwise I forget. Yeah, so that way that solves that IO control error that you're bound to get on a newer kernel. Okay, so that's it. It's configured. This is how easy it is. Let's configure also the startup to start up nice and big already, because size does matter. And you need to fill in one of those valid numbers, 2950. Okay, so now when we start this, it will be a big blinky, 1170 blinky. Boom, that is a nice big panel, and we like big panels, right? So it's running. Now we're going to create some code that I've already written over here. So let's quickly run through this, and we will enter it in the front panel. Move 100,000 octal into R0. R0 is a general purpose register. R0 to R5 are general purpose registers. Then I do a little cheat I call the reset here. Now reset gives a 70 millisecond timeout, because otherwise it was completely all on, basically, very dim. I didn't want to bother by actually doing another immediate 12701, say 7777, do a decrement of R1 and branch not equal 13 something or 1 3 something. I was like, and a jump subroutine in RTS, so I figured let's do this. Don't use this on an operating system. A reset bus on an operating system like RT11, it's bad practice. You don't want that. Then we have a clear carry that is required because we set bit 15 high and we're going to rotate it to the right. And since bit 15 is high, the carry is set. So you would shift in that carry as well. So you get all these LEDs that are on, and then it's just on. Then we're actually going to rotate to the right the value in R0. So we set that 1 in there, 1 0 0 0 0 0. We scroll that to the right. We compare if it's 1, if it's here. If not, branch not equal, then we branch back to the reset to the weight. If it is, then again we have a timeout. We do the clear carry again. In this case, it's not needed because we don't set the carry here. But it made it a bit easier to enter because then it's symmetrical. And it's not really in the way that 9 microseconds. We can do with a lot more slowdown to actually see what we want, because we have an angry KITT scanner. And then we rotate up, so we go there, 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 there each time we call, and we compare if this is set. If not, then we continue scrolling up. If it is set here, then we branch all the way back up to the reset. And then you have your scanner up and down. And we're going to add that in octal. I already worked out the opcodes, because that's the level of abstraction that we have. We only have a switch. The only thing closer would be to have a battery with a wire and tapping on the pins of the CPU. That is the only physical abstraction that we can go lower than this. Right, so let's program these opcodes in. And I'm bound to make a mistake. I will fix that off screen then, but I will show you how it's done. So first we hold the system, right? It stops running. And then we need to load the address where I want to start this. And I want to start this at 1000. It's an arbitrary number. So 100, 1000 hex, load. Right, we can examine what is in there. And there is some bytes in there, but not what we want to add. We want to add 12700. So I always start from the right. It's far more convenient to go 0, 0, 7 to 1. And then we have 12700. That's so convenient, and we just deposit this into the system. Oh, 007. Yeah, better safe than sorry. Check. There we go. We deposited. We switch the switches off. Now the client where I did this actually, I entered the bootloader for the disk in the front panel because they had a power outage and their mumps didn't start and
They had a piece of paper on there, and they otherwise needed to call the company delivering this stuff. And I saw these opcodes, and I was like, this is very much like the 6502. I look at the panel, makes sense. And the little sheet, I can do this. And that ruler that they put in there had their branding on it, the company, and it's to push down all these switches in one go. That was kind of convenient, right? So we now need to enter this 10,000. Now you would be inclined to say, okay, we just loaded 1,000, so let's load 1,002. And let's set 100,000 in their deposit. And this will work, but it will take a lot of time actually flicking all these address switches, and you would go wrong. Sooner or later, trust me, been there, done that. So an easier way is just to continue adding these opcodes. Deposit and see, it updates that address for you. So we're now at 5, so 2, 2, 4, 1 deposit. And deposit takes what we put on the address bus, on the data bus on that address. 241 0006 deposit. And this way you can enter pretty quickly some very 722. You shouldn't talk and do this, trust me. You can enter some pretty big applications relatively quickly, yeah. And then we need the 1. This one is basically the second word. It's the operand of this opcode. So 2, 7, 3, 1 deposit. And I wish I had that ruler to just flick them all down in one go. And then we have 5 deposit. And see, those addresses just increment automatically. There's no worrying for this. 241 deposit. 0016. And going from right to left is so much more convenient than going from left to right, since it's a little engine. 00722. So 22700, yes, deposit. And now we deposit 100,000 octal deposit. Yeah, it's a nice 16-bit machine. I really love it. Even though I didn't do too much with PDP11s. I had one and I wanted to install BSD on it. Couldn't find the disks back then. So I gave it away to my colleague. On September 11th, I said, you can have it if you carry it out. It was a whopping 45, maybe 50 kilograms. And even though it was a micro PDP11. And he gave it away, I heard last year, to another colleague. And he's still running it with the same MFM 20 megabyte Seagate disk in there. It's incredible. So 2731 deposit. And this is the only tedious thing, flipping them back. Jumps are sort of weird. The base operating opcode is 400, and you add the relative offset. So 377, that is 255. That is the highest that you can go. So basically this instruction, same instruction. 376, and you add that together. So 400, in this case, 363. That jumps all the way back there. So you add them together. That is the only thing that always tripped me up a little. Coding these 6 and 7. Let me check. 7, 6, 3. Okay, deposit. Now it's a good habit to check. So load. If I have any errors, I fix them offsite and get to the running code. Load. Examine. 1, 2, 7. That looks good. Then we have 10,000. Yes. Then we have 5. Yes. 1, 4, 2. Yes. 6, 0, 0, 0. Yes. 22700, yes. 1, yes. 1372, yes. 5, yes. 142, yes. 0016, yes. 22700, yes. 100,000, yes. 1372, yes. And the all important jump back. This is where you really can go wrong. 3, 6, 7, yes. Okay, so let's load back that 1000. Toggle the hole to enable and start. And there we go. We have the angry KITT scanner. This slowdown is a bit because of the system. It sends basically network messages, remote procedure calls over network. So really quick changing things is not the most ideal, and it really hogs your CPU, as you will see. If you run an htop, simh is really hogging it. And that's the PDP11 realcons. That's the real console extension that we just installed. That is from the BlinkenBone stuff. So it is kind of heavy, but if we hold it, then it just shouldn't do anything anymore, and it should just drop. And if you don't use these panels, then you're pretty much fine. I think that even the execution takes precedence over the application. But there you go, the angry KITT scanner.
So there you have it. You now know what it's like to enter programs back in the 60s and the 70s. Now the PDP1170, I believe, don't quote me on it, this version was from 79. And you cannot go a whole lot lower in abstraction wide. What I said, you can have a battery and wires and actually tap the PDP11 CPU with the signals. But that's about the lowest that you can go in the physical world. And that's what I love about these machines. They're so low level, so accessible. You can understand everything about them. Today with these x64 machines, it's just abstraction on abstraction, security on security. You cannot even do self-modifying code anymore on these machines without a massive box of trickery that you need to pull open. It works on those machines. So I love these old machines for that reason. They are so controllable. And yeah, the PDP11, it's a classic. Now I said I owned a PDP11, and that was the micro PDP11, and it was from 1989. I got it myself in 1996 from Brunel, where I worked back then, because it had been used for the card access to the building. So it had all these terminals to the card readers that used serial. So yeah, that was kind of a cool machine, and I wanted to actually run BSD Linux on it, Unix on it. But I couldn't find the images. I looked for them, and in 2001, it was just standing there, and when I switched it on, it was really, really loud, even though it's a relatively small machine, like this big and that tall. It was really, really loud. So I said to a colleague of mine at IBM at the time, and I know when it was 9/11. Because when we came home, I saw the buildings collapse. I said, you can have it for free, but you lift it out of my apartment. Because it was still a massive 45 kilograms, which is quite hefty. I said, and I even throw in a Chinese dinner. And he was like, oh my God, this thing is huge. It's like wrestling a refrigerator, only a bit smaller. So the two of us, we lifted it in his car. I still treated him on the Chinese. And he already found some disk images, installed it, ran it. And we hadn't spoken until last year for about 20 years. We come across each other on LinkedIn. We talk about his kids. We're now, of course, adults. And then we talked about the PDP. And he said, no, I don't own it anymore. I gave it to another colleague of mine or a friend of mine. He's still running it. He's using it for data acquisition of a system that he used in the past. And that same old 20 megabyte Seagate MFM drive that is in there is still working. Unbelievable. Unbelievable. And it's now running every single day. So that's kind of cool. These were great machines. Yeah. I now understand why my dad had such a passion for them. I only used them with the mums language. We had one customer that had it with mums. Like I said, with the ruler, we had to boot it up. Other than that, I never used them extensively myself. But I do like them. So I hope you learned something and see you in the next one.